Good morning, everyone. My name is Gordon, and I will be talking about upgrading Apache Flink applications. What is the state right now? How are things looking? So ever since Flink 1.1, we had save points, and users could use these save points as a baseline feature for them to carry state from one execution to the next execution. And this for many different purposes, mostly for, let's say, cluster upgrades or bug fixes or whatever. But ever since we introduced save points, we have been starting to think about more quality of life improvements for people to manage this in a more smoother way. And so today I'll be going through what people have been thinking about and what are the approaches that are currently being discussed in the community at the moment. And it's not moving. Hang on. All right. So ARTISANS, it was founded by the original creators of Apache Flink, I think 3 or 4 years ago, and we are also providers of a solution called the D8 platform, and we also have a recent announcement this morning on updates of this product. So first going over overview of the general concerns of long-running services, especially streaming applications like Apache Flink. What are the general concerns that you would or should think about when you're doing this operation? So just a very quick recap of the baseline feature of what save points provide for users. So you have your running Flink user code job, and this user code would interact with the local state backends, manipulate the state in there, and on every checkpoint, you would Flink would persist all these state into a central DFS as state bytes. And this would form a save point in this DFS. And then you would upgrade your job. This upgrading of your job could consist of any kind of specific reason. For example, you're upgrading, most simple, you might be upgrading a Flink cluster, you're fixing bugs, or your pipeline topology changes for any business logic changes, for example. Or you reconfigure your job. Now, by this reconfiguration, it could mean changing parallelism, or you would want to swap different state backends, which isn't available right now, but this is what I'm going to go through in a sec. So you would want to maybe change your state backends because you've realized that memory-backed state backends just isn't enough for you. And then that state schema. Your state schema would evolve. You would expect it to evolve as your business logic changes. So eventually you would need to change that, and that would also incorporate implications in how your state serializer was designed. So a sixth part isn't really a concern when upgrading this, but is something that users have been asking for, which is a dry run or a offline check of whether or not this upgrade is actually compatible. So right now, if you're actually running in Flink in production, and for any reason you upgrade this job, you only realize something is wrong when you actually run the job, and then all the task managers just launched, and that's just not really nice. So from the save point, we reload state into the local state backends, and then we proceed with the computation, which continues to manipulate the state in the state backends. So this is the basic pattern of taking a save point and then restoring. Okay, so what's already, or let's say almost available? So I think since 1.3, you could already change the operators in your topology. For example, you could remove operators or add new operators. And Flink, even if you change, for example, a series of chained operators, and you change the sequence of the operators, the state restore will still be able to work as long as the operator UIDs are matching. So on the restore, it would find operator state and the operator that needs to load this state into by using the UID matches, matching by UIDs. So this is already available. Job reconfiguration is also, I think since 1.2, we can rescale jobs, change the parallelism of a whole job or a single operator. What users have been asking for is the swapping state backends. This is actually a very low-hanging fruit, a feature that could be developed, I can't say a time frame, but but this is something that is a very low-hanging fruit, as in it could be available anytime soon. it's actually very simple. It's just we need to unify the Savepoint formats between the different state backends. So right now they have a slightly different state format. This would also be related to this another feature that I'm going to mention right now, actually. So what have users, those were what is already available, then what have users been actually asking for? So most importantly, state schema migration. How do I adapt my state schema to new business logic? Second of all is Savepoint Manipulation. Now this is, when we actually reach this point, you will realize it's going to be a very powerful tool, in my opinion. So what would this enable? For example, recalculating any state. So you might have some bugs in your user code. If it's just some simple bug, then all is good. But if it is a bug that causes your state to actually be wrong, you would need to recalculate the state. Now, up to now, the most straightforward solution, well, not really straightforward because it's sometimes not that easy, is to replay your whole stream and to rebuild a state with your new fixed code, right? But sometimes that's not really easily available. So we might sometimes want to just, okay, this is my save point. I know how to calculate the actual correct state from the save point and then use that instead, okay? Another possibility is state bootstrapping. So we had some talks in San Francisco, and also I think some talks in this conference in Berlin this time about how to bootstrap state, and everyone is using their kind of own technique on trying to do this. So the community has been discussing this, and also in my own opinion, something like a tool that would enable users to actually create a save point from some data in some external database and then bootstrap this as an actual save point and resume from that would be the most straightforward way. So this is, we will discuss this in a sec. And also what I mentioned, upgradability dry-runs to check this. And basically this boils down to whether or not there is a tool that I can just take jar 1, which is the old code, jar 2, compare them, and tell me if there is any incompatibilities I should be aware of. Okay? So we'll go through these three, and first of all, state schema migration. So, as I mentioned, the schema of your state will grow. You should expect it to grow. And the schema is actually determined by the serialization format of the actual state serializer that serializes the state. So it is complicated in a way that the reason of the complication is rooted in the fact of how different state backends serialize. The timeliness of their serialization is actually different between different state backends. So what does this mean exactly? So this, in heap-based backends, we have, so let's say we have computation, and this computation covers 5 keys. In the heap-based backends, all the state objects are kept as Java objects within the JVM heap. And when you manipulate these keys, states, it's basically just manipulation, changing what you do with Java objects, basically. And let's say right now in the first execution, we're using serializer version 1. When you actually do a checkpoint, this serializer version 1 would be used to write all these, serialize them, and be serialized into the save point. And they would be of schema version 1, let's say. Now you want to restore from the save point, you upgrade your job, and this upgraded job now uses serializer version 2 for this specific state. Okay? And when you restore, these state bytes are deserialized into the state backend, back into the state backend, and then you proceed with your computation. Now the catch here is that all we need for this restore to be successful is that we have serializer version 1 somewhere around and available. Once this happens, everything is back to Java objects. We can continue with whatever we need to do. But when we now take a save point, it is now serialized by version 2 serializer. So then the serialization schema in the save point would be all of version 2. Now, with this in mind, what basically this means is by nature, heap-based state backends, the process of taking a snapshot, restoring, and then taking a snapshot again is itself already a state migration. The only requirement is that at restore, we already have the previous state serializer available at restore time. What this means is, if you're familiar with the life cycle of Flink operators, an operator first restores all these state bytes. That's called the restore and a state initialization phase, before any user code is actually executed. And right now, the way state declaration works or state registration works is that it is part of user code during runtime. So state is registered during runtime. So at the restore phase, we have no idea what the new serializer would be like. This is how it currently works. So we need the old serializer around. And to be able to do that, what Flink currently does, which actually isn't a very good idea, I'll explain later, is that Flink currently writes also the state serializer into the Savepoint using Java serialization. And when we restore, we also use Java serialization again to read the serializer and then continue to use this serializer to read all the state bytes and then load this into the state backends. Okay? One other thing, if you're not familiar with this term, I very commonly often use this. So it's lazy serialization and eager deserialization is how I characterize the serialization behavior of heap-based backends. So by lazy serialization it means that we only serialize stuff when we take a save point. By eager deserialization means when we restore, we have to deserialize right on point as part of the restore process. Okay? Right, so moving on to off-heap backends. For off-heap backends, it's different in that state kept in RocksDB is all just byte arrays. So what happens on each state access is that a serialization, deserialization round trip happens on every state access. And when on checkpoints, all that happens is that we just transfer all the files of all the SSD files into as part of a checkpoint. And when we restore, let's say we also upgrade the job to be serializer version 2. What happens now is this: on restore, we still transfer all the state bytes. Right now it's version 1. The old serializer actually is never required to be used as part of this restore process. When we continue with the processing, we would only use version 2 for all the state accesses. So let's say now in this specific execution, we only need to process key 2 and key 4. Now, when it accesses it and then rewrites upon update, this specific keys would now be in version 2. Okay, and now let's say we take a checkpoint and this all will be transferred into a discrete file system. It gets even more complicated when, let's say, on the third execution, we change to serializer version 3. Then now the save point would potentially have 3 versions of schemas within there. Okay, so this is where it gets very complicated on how to implement a general state migration procedure within Apache Flink. So to wrap that up, eager serialization and lazy deserialization is completely opposite of heap-based backends. Eager serialization, as in state is serialized on every access, but it is not deserialized and serialized on restore, but also on state accesses. Now, the requirement now would be that the new registered serializers need to be compatible with all previous schema versions. It's not just the past executions version, but all versions that you know might be in the state save point. And as I mentioned, this is because since data will only be in the new version if it was accessed and it was written with a new serializer. So it is important for this scenario to have a fully backwards compatible serializer that ensures jobs could proceed safely, especially if you're using out-of-core state backends. And Flink has some methods that allows you to ensure your serializer implementation can can do this, and I'll explain this, I think, in the, no, okay. So what, just a little bit more detail, what would contribute to a actual state serializer upgrade? If you're familiar with Flink's serializers and how it extracts types and how it generates serializers for the types, this is fairly straightforward. If you had a POJO, this POJO had 5 fields. The generated POJO serializer would only know how to serialize these specific 5 fields. Let's say in your new execution, you added some field to your POJO, then the generated serializer would then have, the schema would be different, with regards to that POJO serializer. So if you change your type and you rely on Flink to generate these serializers, most of the time, right now, as the current state in Flink, it would result in a different serializer. Or, more straightforward, you provide your own custom state serializer and you change that. Changing by, you have the same serializer class, you modify something inside, or you have a completely new serializer class. Okay, so these all would be possible. And right now, in Flink, as of Flink 1.6, which is the newest version, we still don't have a state migration procedure implemented in state backends yet. By state migration, what I mean is a full scan over all the state, all the keys, and then reading with the old serializer and then rewriting with a new serializer. This is required if it's incompatible, right? We need a fresh start of all the schema versions. Yes, so what is the recommended way right now to approach this? This is the current state. In the future, as in maybe 1.7, hopefully, it would be much more simple. So as of now, Flink's auto-generated serializers can only write and read in a single binary format, as in most of the implementations. They only have a single binary format that are defined at the moment. So, for example, as I mentioned, adding a POJO field, it has a new serialization format which is not compatible with the previous one, and it just can't handle this incompatibility. So if you're planning ahead and really want to be safe with this, right now I would recommend having custom state serializers. So what is the, I'll actually have a blueprint of how exactly to implement this fully backwards compatible serializer that you would be safe with. These are the main methods that you would be working with if you care about state migration, state compatibility, and you're implementing your own custom serializer. So besides all the I/O methods, the serialize, deserialize, we have these 2 methods called snapshot configuration, and ensure compatibility. These 2 are called at different points in times. So when we checkpoint the state, we would take a configuration of that old first execution's serializer, take a configuration, and then store that within the save point. Now, this type serializer config snapshot class is actually a I/O readable writable, as in it has methods for you to define how exactly to write this, serialize this stuff into a byte stream. And besides that, we also right now serialize the serializer into the save point as well as metadata. So what exactly is this configuration? This configuration basically is information about how exactly the state was serialized. This information would be carried on into the new execution. When we get the new serializer, this information will be provided to the new serializer and, hey, this is how the state was serialized before. Do you need to reconfigure yourself so that you can read both the current version and also the previous version? So this is the basic idea of the combination of these 2 methods here. So how would you use these 2 methods to implement this fully backwards compatible type serializer? First of all, let's say how you would serialize. So then this would basically boil down to every time you write something into the state, you would want to tag it with a header that identifies the schema version that it was written with. Right? So let's say it's version 2 right now, then you might write int, say version 2. And you always write in the latest binary format of whatever the format is. When you deserialize, you would first read the version identifier and then use this version ID to to know how to deserialize the remaining payload, remaining bytes in the save point. Then, accordingly, what you would do in snapshot configuration is that you return a configuration snapshot that contains all the possible, let's say it's a map, all the possible version IDs that may be in the save point, and also the corresponding information, or let's say it's just, let's just call it schema, of all the versions inside as part of the save point snapshot configuration. And then on ensure compatibility, when the new serializer gets this information from the past execution, it would know, okay, I need to expect these versions, and this is how I should deserialize them. So this is the basic idea of how you would implement this. Okay, this is very tedious and complicated to really get into. So I heard about Avro, I heard about protobuf. Shouldn't those solve most of the problems? The short answer is yes, it should. But then the other side of the answer is there are some implications in Flink that we're currently solving, and they need to be solved first before this actually would work out of the box. By out of the box, my definition is that I just have a Avro type as state, and I can use, I can change this Avro type by any Avro rules that is defined as backwards compatible, and everything should just work perfectly. The main problem right now, if you're really into the details, is that, so as you remember, we use Java serialization to write state serializers into the save point. And now, for example, to be very specific, Flink's Avro serializer currently holds a class instance, a field of a class instance of the Avro type that is serializing. And let's say you change the Avro schema, that would generate a different Avro type class, and with a different serial version UID, and then this would get into the way of Java serialization when we want to restore this Avro serializer. So it's all rooted to the fact that we actually shouldn't be using Java serialization to write the serializers in the save point. There could have been a very workaround fast fix for this, but the community then decided, hey, we should do this properly, and I will discuss how we're going to do it. The main idea that should be fixed is like a prerequisite for an actual state migration story is let Flink save points be completely Java serialization free. Right now, the main pain point is that serialization of serializers. This will, unfortunately, most likely introduce a change in the interfaces related to the serializer compatibility. I'll discuss the potential new interfaces in a sec. And as I mentioned, this should allow Avro types and compatible evolution of Avro schemas to work out of the box. And the second part, after we introduce this, we would also introduce state migration procedures in state backends, which is that full scan, read of old, write of new. And with this procedure, we would be able to allow to upgrade to incompatible serializer schemas. For example, if your Avro schema is completely incompatible, then it should trigger this state migration procedure. Okay. So what is the potential new compatibility-related interface? So I have a link to the Jira. There's discussions going on over there. But just a very brief recap, it's just letting the snapshots of a serializer, which is the TypeSerializer config snapshot, now serve also as a factory to recreate a serializer that is, you can say, is identical or is fully compatible or exactly the same as the original serializer of that snapshot. Okay, so you can just think of it as a factory method to recreate that old serializer. We don't rely on serialization, but we rely on just code instantiating this new serializer. There's a few benefits that this would introduce and get a lot of stuff out of the way. First of all, eliminates the need to write serializers into save points. We only have the config snapshot, which is information about how state was serialized as a single source of truth about the state inside the save points. Also, availability of a resource serializer is determined at compile time. This basically just means you would no longer bump into, because you changed your serializer, you dumped your old serializer class, and then you bump into this class not found exception, which sometimes you just have no idea why this happened, right? So this should solve quite a few problems, and overall just smoothens this whole restore process for, let's say, heap-based backends, because you don't need to rely on serialization to get that serializer. So what would be the changes to the interface? Like I mentioned, in the Savepoint, we should only have this config snapshot in there. We're also thinking about removing this method and moving this to the config snapshot class. This is basically, the main reason for this is just to strengthen the fact that it's actually very dangerous to reconfigure. It's always mostly more safe to keep your serializers immutable instead of mutating the possibility of mutating them. As you remember, if in this ensure compatibility method, sometimes in the current approach, we sometimes need to reconfigure the current serializer just so that it suits the current, just so that it's compatible. This is dangerous because this could easily lead to inconsistencies, let's say, for serializers between, it's the same serializer, but it's in different task managers, for example. So that method, we restore the resource serializer, and that compatibility resolution method is now will potentially be moved to this TypeSerializer config snapshot class, which has also this new restore method. And this restore method would be used to restore the serializer. So the compatibility, the direction is now would potentially be opposite, as in we would provide the new serializer to the config snapshot of the old serializer and ask, hey, am I compatible? If I'm not compatible, but I can be reconfigured, the new serializer instance, without mutating, we don't rely on the user code to actually maybe reconfigure this, but if it's a reconfigured serializer, it's always wrapped in this return compatibility result, and then we use that. This is just for more safer immutability concerns. Okay, so that's basically what you should be expecting maybe in 1.7, and in 1.7, we should have a much better story for Avro to work out of the box. Right, moving on to Savepoint Manipulation. How much time do I have left? Okay. Savepoint Manipulation. So, the ability to read, transform. This is very exciting stuff for me, personally. So, use cases. We would be able to do offline state migration. So what I explained in the past section was that this is migration integrated within the runtime and part of the restore process or part of the state registration process. But with this tool, we might be able to have offline state migration or recalculating user-induced erroneous states or bootstrap new operators with state. But a lot of possibilities here. So, and also point-in-time analytics. You can think of it as you take a save point and you want to analyze what is my state looking, what does it look like across the whole job. Fortunately, we already have some existing community effort on there. It's called Bravo. It was released by King, Gayula from King. And here is a link to, I'm not sure if Gayula is here, actually. Ah, hi. So I'm just going through what he has actually already introduced in this proposal thread. So it's a convenient Flink Savepoint reader writer leveraging Flink's dataset API. So you can think of it as a tool, a set of API that can point to a Savepoint, read that, and then use Flink's dataset API to process it, and then rewrite it to a Flink Savepoint. Or you can have a completely new set of datasets, dataset API, a completely new set of dataset that is calculated from some database, and then use this to write to a new Savepoint. As Gayula mentioned, there are plans to merge the functionality back as long as, so the initial work I would guess would be still on Bravo to make sure it's actually working and it's a proof of concept, for example. And then if we have enough interest in there, which I think already has, the proposal thread has a lot of +1s, it would eventually be merged into Core Flink for tighter integration. This is just going through the example code on the Bravo README. So this is what it would look like, but I'm not sure what it. There might still be discussions on how we want it if we are to merge it to Flink, but it's actually looking already quite good. So we have these utility APIs that we can load some Savepoint, and then use the Savepoint, and then we use this keyed state reader to point to the Savepoint. pointer-specific operator. Okay, so when we process the state, it's always by a specific register state of some operator. So right now we're pointing to an operator called count per key. Okay, and then we read the states in this operator using the value state reader, and we point to the state with a state ID count. Okay, and now this is read as a data set containing all the keyed state of the state under count. Now we can do it. We can do whatever we want with it, with the usual data set transformations. And after, for example, the example here, what it does is that, so this is the data set that we loaded from the Savepoint, and then we can have also define another set of elements. But you can think of it in a real scenario. This could be loaded from some database calculated, and we only want the new counts that we want to be part of this Savepoint that we want to rewrite. Okay, so we join and we get the new counts, and now this is the actual process of writing the Savepoint back. So we have a state transformer, or state builder, and this state builder, what it basically does is that we need to know how we need to first serialize the new counts, and also join it or union it with the original state, and then rewrite everything back to the Savepoint. And then you can also just spawn a new job with a Savepoint. Okay, so this is the basic idea. If you're more interested, you could also talk to Gayula or go to this thread here and their repo. Okay. This is actually very quick. Upgradability Dry-Runs. So what this is about is the ability to detect incompatible upgrades offline. Now, common incompatibilities would be, I messed my topology up. Well, you can't really mess it up too much unless you change the key partitioning or completely change the ordering of two operators, but sometimes you still might bump into this. And incompatible state schema changes, this would also most likely, if you don't want to perform some state migration, this was unintended, you would want to know about this. So the possible approach, this feature is something that some users asked me about offline, and there is no discussion going on in the community yet on this specific feature, but I thought it was nice to bring it out. So the possible approach to do this compatibility check would be to just check two stream graphs generated from two job jars. And because the logical plan of the streaming pipeline is already encoded in the stream graph, checking topology incompatibility should be quite straightforward. But what about information about registered states? Can I just compare the job graphs and know that some registered state is now incompatible because of the serializer? This is impossible right now because by the nature of the information about registered states is currently only visible in state backends. So the way state registration works is that we register it during runtime, so only the state backends will ever know about what state is actually registered, right? So to get to the root of this, what we actually need if we eventually want this feature is that we need something called eager state declaration. But this eager state declaration, a recap of the discussions that have been on this topic. I think this topic was brought out almost a year ago, and there is two different thoughts on it. Some people still need dynamic declaration, and some people think it's a good idea because the API looks fancy. But I think in the end, to my personal opinion, I think we would have both, but some features would maybe be limited only to if you're completely using eager state declaration, for example. But what the API would look like, this was actually something I came up with during one of our data artisans internal hackathons on some topics that we know users have been asking for, and we just hack something out. But I think it would look something like this. We would define state. And if you're familiar with the declaration of state, you would actually have a descriptor, and then you provide this descriptor to a get runtime context to actually get the state handle, right? And this API, what it does is actually we combine the state descriptor information, which is like the state ID or the serializer of a state or whether or not it's curable, together with the actual handle to access state. So as you can see here, this value state, we provide the serializer and stuff, and we also use it to access. Now, the important part is we annotate it with this annotations. And this basically tells Flink, this is keyed state, this is operator state, or whatever. And this is analyzed when we generate the stream graph. Because we have these annotations now, we can know, OK, the user actually wants to use keyed state, and this is the information for the keyed state, or the operator state. And this could even get more interesting if you have used union operator state or broadcast state already, you would realize that once you say this state is union list state for operator state, you cannot change the redistribution scheme anymore, right? Because that is hard-coded within the Savepoint. But theoretically, it should be possible that you can change this redistribution scheme on any execution attempt that you like. And this should be as simple as just saying, OK, now in this execution, I want my redistribution scheme to be union or broadcast or the partitionable round robin. OK. So wrap up. Basically, ever since Flink 1.1, we had save points. We were happy with it, and then we're not so happy with it. We want more. And the community is definitely very is keeping a close eye on what we should do to smoothen or the process or enable more possibilities for this. And right now, of the most importance would be the state schema migration, and we should be able to expect something, a solution there, even if it's very minimal for 1.7. And also something very exciting would be this reading from transforming, writing to creating save points. I would recommend anyone who is interested in this to try Bravo out. And I would also love to hear more about your pain points on upgrading your upgrade story, and let me know if there's anything that's still bugging you. OK, that's all for today. Thank you. Do you still have time?
There's still time for 2 questions. So if you have any questions, raise your hand.
Aaron? Yeah.
Hi, I'm Aaron. Question, is there anything to say about Flink SQL in relation to state compatibility?
OK, good catch. So Flink SQL, if you use SQL to generate a streaming job, you take a save point, but you somehow just change the SQL. You change the SQL expression in the new job. It would actually a main pain point right now is that the operators generated the pipeline and the operators generated from a SQL expression. They use, I think they still use the default UID. Yes, and that's one main reason why when we change the SQL expression, we have a new pipeline generated. It doesn't match at all. But on the other side, you could also say that it might not really make sense to have a completely, even if you have select more fields, for example, it might not really make sense to change a SQL expression and expect that state could be completely migrated. Because it's a new expression, the data that it requires is completely different. So you would either need to replay everything, or this might be coupled with this Savepoint input format, output format, read-write functionality for it to be actually working. Yes, but yes, SQL right now. The guarantee is that within the same Flink version, it should always be still working. We have fault tolerance. We can restart an execution from a past SQL, and as long as the SQL stays the same, SQL expression stays the same. I think across Flink versions, the compatibility isn't guaranteed, because sometimes cross versions we also change how optimizations are done, and the operators are also maybe different. Yeah. Is that correct? Yes, it is. Yes. Yes.
One last question. Well then, thank you very much.
Okay, thank you.